In today's lecture, we will talk about something called infinite series. So, what is an infinite series? Suppose I have numbers, real numbers, a1, a2, a3 and so on. It's an infinite collection of numbers, and I want to talk about an expression of the form a1 plus a2 plus a3 and so on. That means I am not stopping. All these I want to sum up. So this gives an expression of this form, summation n from 1 to infinity an. This is called an infinite series. Since there is something called infinite series, there should be something called finite series also, but usually we don't use the term series for finite things. So I can also look at something like summation n from 1 to k an. The meaning of this is very clear. What we mean is that this is a1 plus a2 plus so on up to ak. This has a well-defined meaning. I have k many real numbers. I am summing them with each other. But when you go to the analogous thing for infinitely many real numbers, then the question makes sense that what do we exactly mean by this expression written here? Because this is going to be an infinite process, because I am not stopping. You see, this sum is going on and on and on. But then finally, do you land up with something when you go on summing it up? So naturally, there is a question of well-definedness of this kind of a sum. So what do we mean by that this summation n from 1 to infinity an makes sense? So the question is, summation n from 1 to infinity an, when is this sensible? That is, what is the meaning? For example, I can start looking at an equals to 1 for all n. Notice that if I look at summation n from 1 to k an, what I get is 1 plus 1 plus 1. This is k times. And what I get is k. So this has a well-defined meaning. But then what is the meaning of summation n from 1 to infinity an, where an equals to 1? What should this mean? Now intuitively you can see that what is going to happen is 1 is getting added to 1 once, producing 2. Then again 2 is being added to 1, producing 3, and so on. It goes to produce 4, 5, 6, 7, 8, 9, and it goes on. So you can intuitively feel that perhaps this sum, if at all makes sense, will produce something like infinity, which you don't really want to deal with. So you want to know that is there any sensible way of defining summation n equals to 1 to infinity an, so that for certain choice of an's, it ultimately will give me a real number. That we will call the infinite sum of these numbers an. So we start with definitions, but for that I need some notations first. So we define s of n to be equal to summation k from 1 to infinity, 1 to n ak. So I look at the numbers a1, a2, an, which is given to me, which I am supposed to sum up infinitely many times. I fix any n, then I look at the sum of first n terms, that is called Sn, which I have written here. So this is called the nth partial sum. Notice that finally then from the numbers an, which I have started with, a1, a2, a3, so on, this was given. From this I have produced Sn, where n is a natural number, and Sn equal to summation k from 1 to n ak, which is a sequence. This is a sequence. Then what I can talk about is the limit of the sequence, if at all it exists. Sn is just an ordinary sequence of real numbers. I will say that the sum makes sense if the sequence Sn converges to some number s. So now I come to the definition. Summation k from 1 to infinity ak is called convergent if the sequence Sn of partial sums is convergent. In other words, the definition demands that the summation nk from 1 to infinity ak is a sensible infinite sum if the sequence of partial sums of that infinite series, which we are denoting by Sn, is convergent. So here I will note where Sn is summation k from 1 to n ak. So how do we check when an infinite series makes sense? Very simple. I fix an n. Then I look at the first n terms of the infinite series. I sum them up. I call it Sn. Now I am varying n, right? So I get a sequence. Now I just test whether the sequence Sn converges or not. Because given a sequence, we know how to check the convergence of that sequence. Whatever method we have, sandwich theorem or whatever, we will use that method, or even if we can somehow show that the sequence of partial sums is Cauchy, then by one of our previous theorem we know that the sequence converges, and hence the infinite series will make sense. So the process is very simple. I will repeat once again that given an infinite series summation k from 1 to infinity, what you do is first you look at the case n equal to 1. Then what is S1? S1 is just A1. Now you fix n equal to 2. Then what is S2? It is A1 plus A2. Fix n equal to 3. Then what is S3? It is A1 plus A2 plus A3. I go on doing this. If n is equal to m, then Sn is A1 plus A2 and so on up to am. So finally this produces a sequence Sn. I just want to check whether this converges to some limit s. If it does, then we say that the infinite series converges. Now let us see, by this definition, does any infinite series at all converge? Okay. So we start with this infinite series. So this is our first example. Let us look at summation n from 0 to infinity x to the power n, where x equals to, where modulus of x is strictly less than 1. Now this is an infinite series. X is a fixed number. X is not varying. In particular, if you like, I can choose x to be equal to half, or I can choose x to be equal to 1/3. So in particular, if x equal to half, I am looking at the series summation n from 0 to infinity half to the power n. Okay, so that makes sense. I want to see whether this infinite series converges at all by the way we have defined the convergence of an infinite series. So what we have to do for that? Well, we have to look at the sequence of partial sums and try to see whether they make sense. Okay, so I define Sn equal to summation k from 0 to n x to the power k. So this is actually 1 plus x square up to x to the power n. Okay. Now this being a GP series, I know how to calculate this sum. I know that this is simply 1 minus x to the power n plus 1 divided by 1 minus x, as the given one is a GP series. Okay. Now I have to check what happens if I take the limit as n going to infinity of Sn. That means I am looking at limit n going to infinity 1 minus x to the power n plus 1 divided by 1 minus x. Now x has nothing to do with n, so I get that this is 1 minus limit n going to infinity x to the power n plus 1 divided by 1 minus x. Now notice from our knowledge of sequence that we know that this fact is true, that if mod x is less than 1, then limit n going to infinity x to the power n plus 1 is actually equal to 0. So by this I get that this is 1 by 1 minus x. That means the infinite series summation n from 1 to infinity x to the power n, which we are going to look at, this infinite series actually converges by using the definition of the convergence of this infinite series. Okay, there exists a particular definition, so I am just checking that this infinite series satisfies this criteria of convergence which we have defined. So in particular, if I choose x equal to half, it then implies that summation n from 0 to infinity half to the power n, that is equal to 1 by 1 minus half, that is equal to 2. Now let us see some more examples. Let us look at this infinite series summation n from 1 to infinity log of n plus 1 divided by n. I want to check whether this infinite series converges or not. So I define Sn, that is summation k from 1 to n log of This I can certainly write as summation k from 1 to n log of k plus 1 minus log of k. If I open it up and write down, we immediately see some cancellations happening. That is, if I put k equals to 1, plus k equal to 2, so log 3 minus log 2, plus and so on, then the last term is log n plus 1 minus log n. Now if I do look at the cancellations, what I am going to get is log n plus 1 minus log 1, which is 0. Now if I want the infinite series to converge, then I must have my sequence of partial sums Sn to converge. But here, what is the sequence of partial sums Sn? So finally the sequence of partial sums which I got is the sequence log n plus 1. This is my sequence Sn. This is the sequence of partial sums. Question is, does this sequence converge? Well, we again know from our knowledge of sequences that if a sequence converges, then it is certainly bounded. No unbounded sequence can converge. But look at the sequence log n plus 1. This is certainly an unbounded sequence, and hence it does not converge. So this does not converge. As Sn is an unbounded sequence. Okay, so this infinite series does not make sense. Now we are going to define again, so it is definition. If summation n from 1 to infinity an converges, then let S be the limit of the partial sums. If the infinite series converges, that means the sequence of partial sum converges, and since the sequence of partial sum converges, it converges to the unique real number which I called S. Then S is called the sum of the infinite series, and we just write it in this form, that n from 1 to infinity an, we just define it to be equal to S. So in this light, we have already proved that summation n from 0 to infinity 1 by 2 whole to the power n is actually equal to 2, because we found out that the partial sums which we have constructed use GP series to explicitly evaluate it, took limit and found that the limit is actually 2. So by the previous definition, the sum of the infinite series is 2. Then it suggests the following easy exercise. You should check it yourself, that summation n from 1 to infinity half to the power n is equal to 1. Check it yourself, which should be true, but I want you to check this the following way. Find first the partial sums. Calculate the partial sums if you can, then take the limit, show that the limit is 1. So this powers of half, if you go on adding to itself, what it produces is 1. In the same light, if I look at this example, this is a bad infinite series. Summation n from 1 to infinity log n plus 1 by n has no sum because it does not converge. So we can talk about sum of an infinite series if and only if it converges. Now the next question is, which infinite series actually converge? How do you understand that? Looking at the coefficients appearing in the infinite series. That means I will just look at this expression summation n from 1 to infinity an. I will just look at this expression. Then from these ans, I will like to conclude whether it converge or it does not. When does it converge? Can we find it out from the behavior of the ans? That is the question. The elements an which appear, is there any property of those ans which will tell me that the infinite series converge? So for that again, we look at the partial sums, that is Sn, that is summation k from 1 to n ak. If summation n from 1 to infinity an converges, then there exists S, a real number, such that Sn converges to S. Now comes the following trick. Notice that Sn minus Sn minus 1. What is this? If I write down the quantities A1 plus A2, it goes up to An. From this I subtract A1 plus A2 plus An minus 1. I have just written down the definition of the partial sums. Then everything gets cancelled, only what remains is An. Then what is limit n going to infinity An? This is same as limit n going to infinity Sn minus Sn minus 1, which I can certainly write as limit n going to infinity Sn minus limit n going to infinity Sn minus 1, because both the limits exist, which is s minus s, that is 0. So we get the following theorem, which is an interesting criteria. If summation n from 1 to infinity an converges, then limit n going to infinity an is 0. So you take an arbitrary sequence an and try to sum them up. It will not work out. At least if you want to make sense of it, you have to take sequences which converge to 0. Otherwise there is no way that the infinite sum makes sense. Okay? Now let's look back at the example, the bad example. Summation n from 1 to infinity log n plus 1 by n. Look at this. I know that this infinite series does not converge, that we have proved. Okay, but what is limit n going to infinity? Log of n plus 1 by n. Notice that limit n going to infinity, n plus 1 by n, that is 1. That means if I take log, then this limit is 0. What does it say? That the infinite series summation n from 1 to infinity log n plus 1 by n, this series has the property that its terms converge to 0 as n goes to infinity. But still the sum does not make sense. Does this contradict the previous theorem which we have proved? Let's look back at the previous theorem. What does this say? It says if the infinite series summation an converges, then the terms converge to 0 as n goes to infinity. It does not say that if the terms converge to 0, then the infinite series converges. So this theorem which we have proved, that convergence of the infinite series implies an converges to 0, in which way this result can actually be used? This theorem can actually be used in proving the fact that certain infinite series does not converge. You just show that the terms of an infinite series does not converge to 0. You just show that. That will immediately imply by this theorem that the infinite series does not converge. So how to use this result is this. So the typical application of this result is the following. If limit n going to infinity an is not 0, then summation n from 1 to infinity an does not exist. In other words, summation n from 1 to infinity an does not converge. So in the technical language, that the terms of an infinite series going to 0 is a necessary criteria for convergence of the infinite series, but it is no way sufficient. Now we come to some important infinite series which we will encounter time and again, and then try to devise a procedure by which we can test whether an infinite series converge or not, because we want to produce examples of many infinite series, and there should be some handy rule by which one should be able to check whether an infinite series converge. For this we need to study some infinite series which converge and then deduce informations about other infinite series from these infinite series. Okay? Now we are going to look at some fundamental infinite series which will keep appearing time and again. First, let us look at this infinite series summation n from 1 to infinity an, where an equals to n. Okay. Now you go by the direct method of finding the partial sums, or by the previous criteria, you will get the same result, that this infinite series does not make sense. It does not converge, simply because limit n going to infinity an, that is limit n going to infinity n, this is certainly not 0. So this implies the series does not converge. Okay. But question is, what happens to this sum, summation n from 1 to infinity an, where an equals to 1 by n. Okay. Notice that limit n going to infinity an, that is equals to limit n going to infinity 1 by n, which is equal to 0. But we know that this condition does not guarantee that the infinite series converges. All we can say is, well, there is some hope that this infinite series might converge because at least the terms are converging to 0. But the question still remains, does this infinite series converge? We will see that the answer is in the negative, that this infinite series does not converge. So that is the thing we are going to show now. So what we do is we start looking at the partial sums. Okay. Now, if I can somehow show that the partial sums that forms an unbounded sequence, then we can certainly conclude that the infinite series does not converge. Because for the infinite series to converge, the partial sums, the sequence of partial sums has to converge. That means at the least that the sequence of partial sums must be a bounded sequence. Okay? Now, to show that the sequence of partial sums, that is an unbounded sequence, what I will do is I will concentrate on a subsequence of the sequence of partial sums and show that subsequence is unbounded. That will certainly imply that the whole sequence is also unbounded. So the trick involved here is to look at which subsequence we will consider that will work for us. Well, we will look at S2 to the power k. That is, for each k, I will look at the sum of 2 to the power k many terms. That is certainly a subsequence of the whole sequence of partial sums. And I am trying to prove that this sequence will prove that this is an unbounded sequence. Okay. So let us see how to do that. So I first start writing down what is S2 to the power k. This is 1 plus half plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8 plus it goes on plus 1 by 2 to the power k minus 1 plus 1 by 2 to the power k minus 1 plus 1 plus and so on up to 1 by 2 to the power k. Here what I do is I regroup terms. That is, this is my first regrouping. I take 1/3 and 1/4, then I take 1/5 up to 1/8. So what is the grouping? From 1/3 to 1/4, what I am doing is I am collecting two terms. Then from 1/5 I go up to 1 by 2 to the power 3. So if I write it in this language, it is 1 plus half plus here what I have is 1 by 2 plus 1, that is 1/3 plus 1 by 2 square. Then what is 1/5? That is 1 by 2 square plus 1 plus 1 by 2 square plus 2 plus 1 by 2 square plus 3 plus 1 by 2 to the power 3. it goes on like this, plus then the last term. You see the pattern here. It is 2 to the power k minus 1 plus 1 by 2 to the power k minus 1 plus 1 and 1 by 2 to the power k. Okay. Now I can easily calculate in each block how many terms are there. So the number of terms in each block, that is 2 to the power k minus 2 to the power k minus 1 plus 1. Okay. So how many terms are here? This is 2 to the power k minus 1 plus 1. Okay. So let us write down what is S 2 to the power k. That is 1 plus half plus 1/3 and so on, 1 by 2 to the power k minus 1 plus 1 and so on up to 1 by 2 to the power k. What I am going to do now is I am going to group terms in the following way. I first write 1 plus half, then plus 1/3 plus 1/4. This is one block. Then comes the next block, which is 1/5 plus 1 by 6 plus 1 by 7 up to 1 by 8. Then starts the next block. It goes on like that. Then finally I have 1 by 2 to the power k minus 1 plus 1 plus up to 1 by 2 to the power k. I can also write it in the following form, that is 1 plus half plus 1 by 2 plus 1, that is 1/3 plus 1 by 2 square. Then the next block, it starts with 1/5, which is 1 by 2 square plus 1 plus 1 by 2 square plus 2, 1 by 2 square plus 3 plus 1 by 2 to the power 4, which is 1/8. It goes on like this. Then comes the last block, which is 1 by 2 to the power k minus 1 plus 1 plus up to 1 by 2 to the power k. Okay. Now, question is, in each block, how many terms are there? Well, sorry, here instead of 1 by 2 to the power 4, I will actually have 1 by 2 to the power 3, which is 8. Now, in each block, how many terms are there? If I want to count, what I need to look at is, so number of elements in each block is equal to 2 to the power k minus 2 to the power k minus 1 plus 1, then plus 1. That is the total number of elements. That is, it is 2 to the power k minus 2 to the power k minus 1, which is 2 to the power k minus 1. So if I take the case, for example, k equal to 3, then I should have 4 terms, which is precisely the case here, 1, 2, 3, 4. If I take k to be equals to 2, then I should have 2 terms, which is the case. Okay. Now, the question is, how many blocks are here? Well, that is very easy to calculate. That my first block is here, this is my second block, this is my third block. So there are actually k blocks. Now look at each of the blocks. For example, 1 by 2 plus 1 plus 1 by 2 square. Okay. Here this is bigger than or equal to 1 by 2 square plus 1 by 2 square, that is half. What is the next term? That is 1 by 2 square plus 1 plus 1 by 2 square plus 2 plus 1 by 2 square plus 3 plus 1 by 2 to the power 3. What is the smallest possible term here? The smallest possible term is 1 by 2 to the power 3. Each of the terms are bigger than 1 by 2 to the power 3, and there are total 4 terms. So it is bigger than or equal to 4 times 1 by 2 to the power 3, that is 2 square into 1 by 2 cube, again half. So if you look at the last term, for example, I have 1 by 2 to the power k minus 1 plus 1 plus 1 by 2 to the power k minus 1 plus 2, it goes up to 1 by 2 to the power k, which is the smallest term here. So it is bigger than or equal to, and since I know that there are 2 to the power k minus 1 terms, it is bigger than 2 to the power k minus 1 into 1 by 2 to the power k, which is half. As a result, I get that S2k, 2 to the power k, then bigger than or equal to 1 plus half plus half. How many halves are going to come? That means how many blocks are there. But I already counted that there are k blocks, starting with the first block which has only one element, half. So I get half k many times. So what I get is 1 plus k by 2. So S2 to the power k is bigger than or equal to 1 plus k by 2. This immediately implies that the sequence S2 to the power k is an unbounded sequence. This certainly implies the sequence of partial sums Sn is an unbounded sequence. Which certainly implies that summation n from 1 to infinity 1 by n does not converge. So this is an example of an infinite series where the terms converge to 0, but the whole sequence does not converge. Now we are going to try to get some necessary as well as sufficient condition for convergence of an infinite series, which will certainly be of theoretical nature, but to develop further practical tools in testing whether an infinite series converges or not, this is going to be very important. So this is Cauchy's criteria of convergence. Of an infinite series. This criteria actually rests on Cauchy's criteria of convergence of a sequence, and hence the name. The idea is very simple. You have an infinite series, summation an. I want to find the necessary sufficient criteria for the convergence of this infinite series. Now, by the definition, this infinite series converges if and only if the sequence of partial sums Sn converges. Now, this sequence of partial sums will converge if and only if it is a Cauchy sequence. This is precisely the idea. So, I will just write that summation n from 1 to infinity an converges if and only if the sequence Sn of partial sums is a Cauchy sequence. Okay. Now, this is implies and implied by the definition of Cauchy sequence, that is, given epsilon bigger than 0, there exists a capital N, certainly depending on epsilon, such that for all m n bigger than or equals to capital N, mod of Sm minus Sn is less than epsilon. Okay. What I have written just is the definition of Cauchy sequence. This is just the fact that Sn is a Cauchy sequence. But what does it actually mean? I can assume that m is bigger than n, or you can, if you like, n can also be bigger than m. Let me assume m is bigger than n. Then this is if and only if given epsilon bigger than 0, there exists capital N such that for all m n bigger than or equals to capital N, modulus summation k from 1 to m ak minus summation k from 1 to n ak is less than epsilon. But if you open up this summation and cancel terms, this is implies and implied by modulus summation k from 1 to m minus n a n plus k is less than epsilon. Okay. This then is if and only if. I can just write it in the following form, that given epsilon bigger than 0, there exists capital N such that for any p and any n bigger than or equals to n, modulus of a n plus 1 plus a n plus 2 up to a n plus p is less than epsilon. I would actually like to say for all p. Okay. So what I have written down here is the case m equals to n plus p. In the previous step, if you put m equals to n plus p, then what you get is precisely this quantity. Okay. So this then implies actually, so this gives me some information about convergence, that if summation n from 1 to infinity a n converges, then given epsilon bigger than 0, there exists capital N such that modulus of this infinite series this quantity is less than epsilon. Why is this the case? Because if you look at the previous quantity written here, this is nothing but partial sums of the infinite series which I have written here. Since the partial sums that is less than epsilon, then the whole sum, since it already exists because the infinite series is convergence, so this sum is also less than epsilon. Okay. So this is called the tail of an infinite series, that if an infinite series converges, then its tail has to be small. One more thing that comes from this is observation 1. The second observation is that changing finitely many terms in an infinite series does not affect convergence, just like sequences. That is very simple. Suppose I have this infinite series A1, A2, AN and so on. Now at finitely many stages, let us say this A2 is changed, AN is changed, some terms here is changed and here is changed to some A2 prime, AN prime, AM prime. Suppose I change these terms. It does not affect the behavior of the convergence at all, because it is not going to show up in the tail. Because what did I say? I said given epsilon bigger than 0, there exists a capital N such that after that term, if I look at sum of any finitely many terms, that is less than epsilon. That is the necessary and sufficient criteria for convergence of an infinite series. There exists a stage is the key here. I will choose my stage, or at least I will search for that stage after this finitely many stages, finitely many points or finitely many numbers which I have checked. For example, this M is the maximum one. I will start looking for capital N which is strictly bigger than M. I will start looking for that. And then check whether summation A capital N plus 1 plus A capital N plus P, whether that is less than epsilon. You see? So the previous terms which I have changed does not matter at all. So that is an important thing which we have learned, that if I have an infinite series and I change only finitely many terms of that infinite series, it does not affect the behavior of the convergence of the infinite series at all. So in the next lecture, we will elaborate on this Cauchy criteria and try to find more examples of infinite series which converges.